Welcome back to the deep dive. You know, for decades, whenever science fiction writers wanted to send people across the solar system, they always fell back on one thing: a long nap. They'd strap the crew into these pods, hit the freezer button, and then wake them up 6 months later at Jupiter or Mars.
Right, you think of Alien with the crew of the Nostromo.
Exactly. Or the pods in 2001, A Space Odyssey. It's the classic trope.
It is, and it's a trope for a reason.
Yeah.
Because for deep space travel, it is maybe the most elegant solution to a whole bunch of really ugly problems.
Well, that's what's so amazing about the material you've shared with us today. This isn't fiction. This is a highly technical stack of sources, all about how engineering and biology are coming together to make synthetic torpor, basically controlled human hibernation, a necessary and maybe an achievable reality for a manned mission to Mars.
That's the key word, achievable. Our mission here is to really unpack this research from organizations like the European Space Agency, ESA, and NASA's partners like Spacework.
And they're not treating this like a fantasy, are they?
Not at all. They're looking at it as maybe the single transformative countermeasure. The one thing that could solve deep space travel's biggest logistical and health challenges. All at the same time.
That's the crucial insight, isn't it? The holistic view.
It has to be. I mean, when you're talking about a 5-year round-trip mission to Mars, and that's the transit, the stay, the return voyage, you are talking about just extreme cumulative stress on the crew, physically and psychologically.
Okay, so if we put propulsion aside for a minute, what are the two main bottlenecks? The two things stopping us from just, launching for Mars tomorrow?
It really boils down to two things: health and logistics. On the health side, you've got this relentless exposure to deep space radiation, and then the brutal effects of microgravity on the body.
On the other side.
Logistics. Just the sheer scale of what's required to keep a human alive for 5 years. That means optimizing for mass, for volume, for power. Every single gram counts.
And the key finding, the thing that ties all this together, is that putting the crew into this torpor-like state, it just fundamentally rewrites the entire equation for a Mars mission.
It does. It's the one intervention that solves problems on the engineering spreadsheet and at the biological level.
Okay, so let's unpack that, starting with the engineering side. If you ask a mission architect, what's the single biggest benefit of putting astronauts into a 6-month deep sleep? They're not going to talk about comfort.
No.
They're going to give you one word: mass. In space travel, mass is everything. It's destiny.
It really is.
Yeah.
The heavier your spacecraft is, the harder it is to launch, the more fuel you need.
Yeah.
It just gets exponentially more difficult and expensive.
So how much of a difference are we actually talking about here?
Well, to put a number on it, we can look at a really critical study from ESA's Concurrent Design Facility, the CDF.
Okay.
They modeled a 6-person crew on a 5-year Mars mission. And the numbers they came back with are just staggering. By using hibernation, they figured out that the total mass of the spacecraft and all the consumables, so oxygen, food, water, all of that, could be cut by roughly a third.
A third? That's unbelievable. How is that even possible?
Well, it starts with how you manage their metabolism. If they're asleep, you completely get rid of traditional eating, digestion, all that. You replace it with something called total parenteral nutrition, TPN.
Okay, so for anyone who hasn't heard of TPN, what is it? What's it doing?
TPN is really the logistical key to all that mass saving. It's a sterile, water-based solution that gives you every single nutrient you need, plus hydration, directly into your bloodstream, intravenously.
So it's a complete meal in an IV bag.
Good complete meal, exactly. It's got dextrose for energy, amino acids for protein, lipids, fats, plus all your vitamins and minerals. The body gets everything it needs, but it bypasses the entire digestive system.
And this isn't some experimental new technology, right?
Not at all.
Yeah.
And that's really important. TPN is a robust, well-understood medical practice. It's used in hospitals everywhere for long periods of time, sometimes over a year, for patients who can't eat normally, like cancer patients or very premature infants. The human body is actually remarkably good at using it.
But the real magic here is how torpor reduces the amount of TPN you need. I mean, if they were just resting but awake, they'd still need a lot of calories.
Oh, absolutely.
Yeah.
But the hypometabolic state, that changes all the math. When you're in that state with a reduced body temp, your basal metabolic rate, just the energy you need to keep the lights on, it drops by about 7 or 8% for every single degree Celsius you go down.
Wow.
So if you hit that synthetic torpor goal of, say, 30 to 32 degrees Celsius, the total energy demand is just slashed. The dosage charts in these sources, they show the daily need for things like dextrose and amino acids is way, way lower in the torpor state than even a resting state.
And that reduction translates directly into cutting the stored volume.
By that one-third figure we mentioned, less energy needed means less stuff to carry.
And it's not just the food that gets smaller. The actual habitat, the place they live, it changes completely if you have 6 people asleep for half a year.
Right, and that change in the engineering architecture is maybe even bigger than the savings on consumables. Think about a standard habitat like the old NASA Transhab concept.
Okay.
It has to have crew quarters, a big galley for cooking and storing food, and a huge dedicated exercise area with all this heavy equipment to fight off microgravity damage.
All of which is bulky, heavy, power-hungry.
And needs constant maintenance. But a specialized torpor-enabled habitat, or TTA, well, it gets rid of the galley entirely. Everyone's fed by Sci-fi. And it gets rid of the massive exercise gear because, as we'll get into, the torpor state itself passively protects your muscles and bones.
So the habitat can just be simpler, smaller, lighter, less power.
Exactly. You're not just saving on food anymore. You're fundamentally shrinking the size and weight of the entire vehicle you have to launch.
Okay, so digging into that, this raises a huge question. How does cutting the habitat and consumable mass by a third change the mission itself? A smaller habitat doesn't mean much if the physics of the journey are still too hard.
This is where the biology actually rewrites the laws of orbital mechanics for a human mission.
How so?
Okay, so Mars missions generally fall into 2 types based on their trajectory. You have conjunction-class missions and opposition-class missions.
Can you break down the difference for us?
Sure, think about it in terms of time. A conjunction-class mission has medium-length transfers, maybe 6 months each way, but you have to stay on Mars for a really long time, like 18 months, waiting for the planets to line up again for an easy trip home.
Okay, so long stay. What about the other one?
Opposition class. That gives you a short stay on Mars, but one of the travel legs is very long and needs a lot more energy, a lot more fuel.
And for any rocket, the big number is delta V, the change in velocity needed. That translates directly to fuel.
You got it. Conjunction class needs less delta V, so it's easier. But that long wait on Mars is a huge challenge. Opposition class needs a ton more delta V because you're pushing this big mass on a less efficient path.
So if you cut the mass of the ship with torpor, you don't need as much rocket fuel to get that high delta V.
That is the key technical finding. The torpor-enabled habitat lets you use these lower delta V, longer duration transfers, the kind that before were only considered okay for, like uncrewed cargo ships.
You gain flexibility.
Massive flexibility. And let's talk about the big metric, IMLEO, initial mass in low Earth orbit. It's the total weight of everything you have to launch from Earth to even start the mission.
The holy grail of rocketry. What does torpor do to the IMLEO?
The change is huge. The sources show that the required IMLEO for a difficult opposition class mission, if you use a torpor-enabled habitat, it becomes roughly the same as the IMLEO for a standard non-torpor conjunction class mission.
Wait, hold on. You're saying that by putting the crew to sleep, you basically erase the massive fuel penalty for the more desirable shorter stay mission.
That is precisely the finding. You make the harder mission type, the one that gets the crew off Mars, faster feasible just by shrinking the life support system. It's a biological solution to an engineering problem.
So what's the ultimate payoff? What does this mean for actually exploring Mars?
The payoff is capacity. The analysis shows that for a given rocket, for a given amount of mass you can launch, the torpor tech lets you send more than twice as many crew members.
Twice as many?
For the same logistical effort. If you were planning to send 4 astronauts, now you could maybe send 8. That's a complete game changer for setting up a research base on Mars.
Okay, let's pivot from the engineering spreadsheets to the biology, because this is where it gets, I think, really incredible. Beyond just saving mass, torpor seems to offer these built-in defenses against the 2 biggest health risks in deep space, radiation and the brutal effects of microgravity.
And these are, and this is no exaggeration, the 2 biological showstoppers for deep space travel. The second astronauts leave Earth's magnetic field, they're just getting blasted by 2 kinds of radiation. You got solar particle events from flares.
Right.
And then the more insidious one, the constant pervasive galactic cosmic radiation, or GCR.
And GCR is the real monster, isn't it?
It's relentless. It's high energy, heavy nuclei just zipping through space. They go right through the ship, right through your body, damaging DNA, increasing your lifetime risk of cancer, cataracts, and what's maybe most concerning, chronic central nervous system diseases.
And we can't really shield against it.
Not effectively.
Mm-hmm.
You need feet of concrete, which you can't put on a spaceship. It's a mass problem again.
So how on earth does just chilling a person down help them survive something so destructive?
The answer comes from research on natural hibernators. Ground squirrels, for example. Studies show that if you expose them to the same dose of radiation, the ones that are hibernating live significantly longer. They have a much higher mean survival time than the active ones.
So what's happening at the cellular level? What's the mechanism?
The leading theory has to do with cell kinetics, cell division. Chilling the body slows down all your metabolic processes, but crucially, it also slows down the rate at which your cells divide.
Okay.
Now, radiation damages DNA, but the real disaster happens when a cell with damaged DNA tries to divide before that damage is fixed.
So you're passing on the error.
Exactly. By slowing cell division, you're essentially hitting a pause button. You give the body's own natural repair mechanisms, all those enzymes and proteins, way more time to find the damage, cut it out, and fix it before the cell tries to replicate.
It's like pausing a factory line so the repair crew can catch up.
It's a perfect analogy.
Yeah.
And we don't just have to rely on animals that naturally hibernate. The sources show this radioprotective effect can be induced in non-hibernators using these synthetic torpor models.
That's the key, right? The bridge to humans.
It is. Researchers took rats, which don't hibernate, put them into synthetic torpor, and then exposed them to a pretty high dose of X-rays. And the results were compelling. They looked at their liver and testicles and found significantly less toxicity and damage compared to the rats irradiated at normal body temperature.
And they found specific genetic markers for that protection.
They did. They saw a clear downregulation of key DNA damage signaling genes, like the gene ATM. It's a major checkpoint protein. It senses DNA breaks and tells the cell, stop, don't divide, start repairs.
And seeing that gene turn down.
Seeing ATM downregulated in the liver and other genes in the testicles, it suggests the torpor state is actively changing the cell's response to damage. It's making it more resilient.
It's like the body goes into a defensive crouch.
Precisely. And there's a second mechanism, too. It's called the oxygen effect. During torpor, your metabolic rate is way down, so you need less oxygen. This creates a hypoxic cellular environment-less oxygen in the cells.
And why is that important for radiation defense?
Because radiation also causes damage indirectly. When it zips through water molecules in your cells, it creates these highly volatile things called reactive oxygen species, ROS.
Free radicals.
Free radicals that cause all sorts of oxidative damage. So by being in a hypoxic state during torpor, you limit the amount of oxygen available, which in turn limits the creation of these damaging ROS molecules after you get hit by radiation.
So it's a double defense. You slow things down for DNA repair, and you reduce the oxygen to minimize the secondary chemical damage.
It's a really robust system. Even just general anesthesia shows some minor radioprotective effects, but when you combine it with the active cooling for deep hypometabolism, the benefits are much, much greater.
Okay, let's connect this to the other big problem, microgravity. Astronauts on the ISS, they have to do hours of intense exercise every single day just to stop their bones from decalcifying like in osteoporosis and to stop their muscles from wasting away. How does torpor just passively solve this?
It solves it by tapping into the biological blueprint of an amazing animal, the black bear. Black bears hibernate, which is a kind of mild torpor, and they stay almost totally still for months. But, and this is the critical part, they don't suffer from disuse atrophy. They don't lose significant muscle mass or bone calcium.
Which is the complete opposite of a human on bed rest. If a person was immobilized that long, they'd be a wreck.
A total wreck.
Yeah.
Human disuse models, like bed rest studies, they show rapid drops in muscle mass, protein, strength. Our bodies are just designed to fall apart without gravity. But the bear, during torpor, it induces what the studies call myriad physiological adaptations that actively protect against this.
So it's not just the lack of movement, it's the state itself that triggers the preservation.
Yes. The torpor state inherently conserves muscle protein. It switches on molecular pathways that stop the breakdown of muscle while also maintaining fatigue resistance and, importantly, preserving bone mineralization.
So all that heavy exercise equipment, the treadmills, the resistive machines.
They become unnecessary. The body's own biology is doing the countermeasure work for the engineer. It's the ideal passive countermeasure for microgravity.
What's so wild about this is that the foundation for this artificial stasis, it's not some crazy new idea. It builds on a medical practice that goes all the way back to Hippocrates, packing wounded soldiers in snow.
That's right. Therapeutic Hypothermia, or TH. It's evolved from that ancient idea into a standard critical care procedure. It's been used globally since about 2003.
And what's it used for today?
Its main use is to reduce the risk of tissue damage from lack of blood flow after, a major event like cardiac arrest, traumatic brain injury, or for newborns who have had a lack of oxygen. The protocol is to induce mild hypothermia, getting the patient's core temp down to about 32 to 34 degrees Celsius.
Okay, but that's mild. For spaceflight, we need to go deeper to get that huge metabolic drop, and that means you have to fight the body's natural reaction to cold.
You absolutely do. The goal for astronaut torpor is a bit cooler, around 30 to 32 Celsius, which is about 86 to 90 Fahrenheit, and you've hit on the biggest hurdle, shivering. Yeah. The body's immediate response to getting cold is to shiver like crazy to generate heat. That's metabolically expensive. It defeats the whole purpose. So to get to a stable torpor, you have to use sedation and other drugs to completely suppress that shivering response.
Before we get into how they do that, what are the current human limits for being in this state? A Mars trip is months, not just a few days.
And the current medical benchmark is actually really encouraging. Humans have been safely kept in a continuous TH state for up to 14 days.
14 days.
Right. That's a solid safety margin built on decades of practice. And what's more, studies show we can tolerate cycling in and out of it. There's one case study of a child who went through 5 separate cycles of TH over time with no observed long-term negative effects.
So the idea of repeated cycles for a long journey is feasible.
It seems highly feasible.
Okay, so let's walk through the 3 main ways they're trying to induce this state. Starting with the simplest, the temperature-based methods. What's nearly ready to fly?
Well, several systems that are already in ERs could be adapted. The first is a non-invasive one, transnasal evaporative cooling. The Rhino chill system is an example. You insert these little catheters into the nose, and they deliver a coolant mist right under the base of the skull.
Why there? Why the base of the skull?
It's just incredibly efficient. You're directly chilling the carotid arteries and all the blood going to the brain. It allows for really fast, targeted brain cooling, which is key in an emergency or for a quick induction into torpor.
Sounds fast, but I can't imagine having coolant blasted up my nose is very comfortable.
You're right, it's not. It can cause stinging, dryness. Patients say it feels oppressive. So for that reason, it's really only suitable for patients who are already heavily sedated.
Which they would be anyway in this model.
Which they would be anyway, exactly. It fits right in.
Okay, what about for more controlled long-term cooling?
Then you look at the established systems. There are invasive intravascular cooling systems, like the CoolGuard catheter. It's a closed-loop catheter that goes into a large vein and circulates cooled saline to directly manage your core blood temperature. Very precise. And then you have surface systems like the CoolA pads that use conductive tech on the skin. They're less rapid, but they're critical for stabilizing the temperature once you're there and for controlled rewarming later. The point is, the basic hardware for temperature control, it already exists.
Okay, let's move to the second approach, chemical and drug-based. This is about using pharmacology to stabilize the state. What are the top candidates for a long space mission?
The leading candidate in the NASA studies is a drug called dexmedetomidine. It's really valued because it has 3 key properties for spaceflight. It's a potent anxiolytic, so it reduces anxiety. It's great at reducing shivering, and critically, it causes minimal respiratory depression.
That has to be huge in a closed environment, like a spacecraft.
Oh, it's essential. You don't want a drug that's going to require complex breathing support for 6 months. Dexmedetomidine lets you maintain a stable breathing pattern even when you're sedated and cooled. For inhalation anesthetics, xenon is also a favorite. It's non-toxic, very stable, but it's also currently very expensive.
Now, what about the Holy Grail? Finding the biological keys to actually switch on hibernation instead of just forcing the body cold.
This is where we try to mimic what hibernators do naturally. And scientists have had some success activating specific molecular triggers. One key finding is the role of adenosine receptors.
Okay.
Using a compound called 5-AMP can induce a hibernation-like state in some animals. Adenosine is basically a sleep and energy-saving signal in the body, so activating it, it's like flipping a master switch.
And the other big one is a gas, right?
Correct. Inhaled hydrogen sulfide, H2S, it's toxic in high doses, but in low concentrations, it's been shown to induce this deep reversible state in mice by basically telling their cells they don't need as much oxygen. The cells go into this low power mode without dying.
It's like tricking the body into thinking it's a bear?
That's the goal.
Okay, and finally the cutting edge. The brain synaptic-based approach. This sounds like something straight out of science fiction controlling the brain circuits directly.
It feels like it. But the research is surprisingly solid. Natural torpor isn't just the body shutting down randomly. It's actively regulated by a tiny group of specific neurons in the hypothalamus, specifically an area called the POA, the preoptic area.
The body's master thermostat.
Exactly. And these neurons are called glutamatergic ADCYAP1 positive cells.
So if you can control those specific neurons, you can just flip the hibernation switch manually.
That's the idea. And we now have these incredibly precise, non-invasive ways to do it. We're talking about remote transcranial ultrasound stimulation, UIH. You use focused, low-intensity ultrasound waves to basically gently stimulate that POA region of the brain.
And what happens when you do that?
The stimulation has successfully induced a long-lasting torpor-like state over 24 hours in rodents, even in animals that don't naturally hibernate, like rats. And the mechanism is beautiful. Activating these POA neurons then inhibits a major part of the body's furnace, the thermogenic brown adipose tissue.
So the brain tells the furnace to turn down and the body just cools off naturally.
Precisely. And they've even identified a specific protein, the TRPM2 ion channel, as being key to this whole effect. This gives us a clean, non-invasive way to induce torpor, which might eventually reduce the need for all the heavy sedation we talked about earlier.
Okay, so we have the tech to put people in stasis. Now comes the messy reality of running a space mission. How do you operate a 6-person ship to Mars when 5 of them are unconscious for 6 months? Especially with that communication delay, up to 24 minutes one way.
Yeah, that operational reality means the mission has to be almost entirely automated. The habitat, the life support, it all needs to be monitored by a sophisticated AI system that acts as the primary caretaker for the sleeping crew. But you can't rely only on automation. You need a human in the loop.
Which brings us to the Sentinel Protocol.
Right. The Sentinel Protocol is the proposed crew rotation schedule. It's designed to make sure at least one crew member is awake and active at all times to be the Sentinel. And it's designed around that medical reality we talked about, that 14-day safety limit for continuous hypothermia.
So how does the rotation work to cover a 6-month trip but stay inside that 14-day window?
Well, for a 6-person crew, they'd do a staggered rotation. Each crew member would spend, say, 3 to 5 days active on duty.
Mm-hmm.
And then they'd go into an 8 to 10-day torpor phase.
Okay, so that keeps any single stasis period under the 14-day limit.
Right. But the trade-off is pretty significant. It means each crew member has to go through up to 15 separate cycles of being put under, maintained, and woken up just on the trip out to Mars.
That's a huge physical toll. But what about the psychological toll on that one Sentinel? You're awake, you're alone, you're responsible for 5 sleeping crewmates, and maybe the entire mission, and help is 24 minutes away.
I mean, that's one of the biggest non-technical hurdles. The pressure on that Sentinel is immense.
Mm-hmm.
They are the only human backup if a system fails, or if there's a medical emergency or a micrometeoroid strike.
Mm-hmm.
They have to be incredibly well-trained, resilient, able to function under just extreme stress and isolation. The sources really stress that picking the right people for this role is just as important as perfecting the technology. That Sentinel's mental health is literally the mission's single point of failure.
And if something does happen, a fire, a pressure loss, how quickly can they wake everyone else up?
Speed is limited by biology.
Mm-hmm.
Based on current medical protocols, the fastest safe wake-up, cycle warming the body from about 90 degrees Fahrenheit back to 98.6, has to be done at a controlled rate of about 4 degrees Fahrenheit per hour.
Which means the absolute best-case scenario for waking someone up is about 2 hours.
About 2 hours, minimum. And that's the time just to regain consciousness and maybe start functioning at a basic level. If there's a sudden critical emergency that needs all hands on deck, that 2-hour delay is a massive operational gap that the AI has to somehow manage.
So that raises the question, what are the biological risks of forcing a human, a non-hibernator, into this state over and over again 15 times?
The biggest risk, the one they call the Achilles heel of hibernation, is immune suppression. When you first enter torpor, the number of circulating white blood cells, your leukocytes, can drop by as much as 90%.
90%.
And in the deep space environment, that's compounded by everything else.
Right.
You combine the torpor-induced immunosuppression with the known immune weakening from microgravity and radiation, plus the fact that some bacteria actually get more virulent in space, the risk of a simple infection turning to a life-threatening crisis is enormous.
And what about when they wake up, the crew finally gets to Mars, they have to do a complex orbital maneuver, start prepping for landing? What shape are they in?
This is the second huge operational hurdle, post-arousal effects. Rapid rewarming from hypothermia is known to cause severe, persistent drowsiness, confusion, slowed reaction times. It's a major problem if you need someone to perform at a high level immediately upon arrival.
So even if the 2-hour warm-up works, they might not be mentally sharp enough to fly the ship.
Exactly. And the faster you rewarm them, the worse the drowsiness is, and that cognitive fog can last for a day or even longer. Mission planners would have to build in a big buffer period after they wake up before they can do anything high stakes.
Okay, let's look at 2 specific spaceflight health risks. First, elevated intracranial pressure, or VIP. It causes vision problems. It's a huge unsolved issue for NASA.
It is. VIP is from fluid shifting in microgravity, which raises the pressure inside your skull and presses on the optic nerve. It's a major risk. But interestingly, while TH isn't standard treatment for this, some recent studies suggest it might actually help lower intracranial pressure in acute situations.
So the torpor state could have this unintended secondary benefit of passively protecting against one of NASA's biggest health risks.
It's a possibility, a fascinating potential synergy that needs a lot more study. But yes, if torpor inherently keeps that pressure down, it solves a huge problem.
And on the nutrition side, you're using TPN, bypassing the gut for months. Does that cause long-term damage? Does the gut atrophy?
This is where the medical data is actually pretty reassuring. There's always an infection risk with a long-term IV line, of course. But studies on thousands of patients on long-term TPN show no evidence that bypassing the gut causes major problems like severe bacterial overgrowth or degradation of the gut lining. The gut seems to stay viable and ready to go once you start eating again.
Lastly, the anesthetic agents. We need them to suppress shivering, but the choice of drug carries its own risks, right?
It's a crucial detail. A lot of anesthetics, especially the inhaled ones, become much more soluble in your body's tissues, your brain, your fat when you're cold.
And what does that mean for the astronaut?
It means the anesthetic builds up more easily and sticks around longer in the tissue. That can seriously delay your recovery time, which makes that already tricky arousal process even harder. You need something that clears out fast.
And there are other side effects, too.
Absolutely.
Yeah.
The sources note that some anesthetics are linked to concerns about neurotoxic effects or cognitive impairment. And long-term anesthesia in general can increase oxidative stress in the body, which can make things like cataracts develop faster. These aren't minor risks. They require very specific mitigation strategies, like using eye ointments or carefully managing the habitat's humidity. Every drug you choose adds another layer of risk to balance. So if we synthesize all of this, we've really moved the idea of human stasis from, a sci-fi dream into a viable, detailed engineering and biological concept.
Yeah, the technology readiness is surprisingly high. We're not waiting for some brand new discovery.
Exactly. We have the core hardware systems, the cooling units, the automated TPN dispensers, even systems to generate IV-grade sterile water in space. They all exist today in some form.
So the gap isn't hardware, it's refinement.
It's refinement. Optimizing the protocols for humans, perfecting the non-invasive induction methods like that ultrasound stimulation, and then doing the long-duration animal studies before you can move to human trials.
And the consensus timeline from the researchers, from NASA's partners, is that a fully automated torpor-enabled habitat could actually be ready for the first human Mars mission in just 15 to 20 years.
We're within reach of that sci-fi future. It's happening fast.
Okay, so let's unpack one last surprising piece of information, and it takes us right back to the biology that started all this. When we think of hibernation, we think of surviving extreme cold, right? Like a ground squirrel in a burrow during a blizzard.
That's the classic image.
But then you have the Malagasy fat-tailed dwarf lemur. It's a tropical primate. It hibernates for 7 months in tree holes where the temperature can get above 30 degrees Celsius over 86 Fahrenheit. It's not about cold defense at all.
It completely inverts the definition of hibernation.
Exactly. For this lemur, hibernation isn't a thermal thing. It's an adaptive energy-saving response. It's designed purely to cope with a seasonal bottleneck when there isn't enough food or water, even though it's warm outside.
It's about scarcity.
It's all about scarcity. So here's the provocative question for you to consider. If the true original purpose of torpor is simply to survive when resources are scarce, and not really about temperature at all, then how much of our perceived human capability, our constant need for abundant food and warmth and exercise, is actually just a side effect of us always having had excessive energy and resources? And what other extreme human adaptations currently suppressed by our hyperfed modern lives are just waiting to be uncovered or induced for our future survival in these new resource-limited frontiers?
Something to mull over until our next deep dive. The ability to endure scarcity might be humanity's next great superpower.
Indeed. We'll see you then.